We need to talk about dating. Believe it or not, archaeologists think a lot about it. C-14 dating, Dendrochronology, OSL dating, argon dating, they all sound like some naughty smartphone apps. But they actually are scientific methods of finding out how old something is, or how long ago it ended up where we found it. And that is very important as we talk about what happened when, or what happened after something else had happened, or what happened in the Cotswolds at the end of the Neolithicum around lunchtime. Today we are so used to being told that stone circle is 4,000 years old, that ditch was dug when Julius Caesar was a child, that we can hardly imagine how, not much more than 100 years ago, people had no way of telling whether a piece of rock was 5,000 years old or 2 million, or a piece of wood found in a lake was put there by their grandparents or some distant ancestors who used only flint tools. Following the reasoning of the Irish Archbishop James Ussher, who put his mighty intellect to work at the question at the end of the 16th century, the whole world was created, as we know, within 7 days, beginning on Sunday the 23rd of October 4004 BC. A notion that we find very strange now, at least those of us who live outside of Oklahoma. To understand most of these modern methods, we need to take a look at the physics of the subatomic world, and trust me, it is going to be fun. But before we go down that rabbit hole, let's first talk a bit about wood. We all know that a tree creates one new growth ring every year. When we look at our firewood before it is split and chopped up, we can tell by counting those rings how old that tree was when it was cut down. Now, if you look carefully, you will see that these rings are not all alike. Some of them are thicker and some of them are thinner, depending on how good a particular year was climatically to put on a nice big extra ring. It's a bit like myself when I look in the mirror. For trees growing in the same climatic region, thin and wide growth rings would occur in the respective same year, and so two pieces of wood coming from the same time in the past can be placed together in time by looking at their sequence of growth ring sizes. Does that make sense? For the sake of accuracy, it is not only the size, but also the relative coloring, the type of wood, the position of the ring within all the rings of a particular tree that are of importance. So the dating of wood by growth rings is a bit more involved than just measuring their width, but you get the general picture. At this point we could start a long, exciting lecture about statistics, but we shall not. Because it is intuitively clear, I think you will agree, that if any sequence of successive growth rings you are looking at is long enough, its pattern of thin, wide, medium, thin, thin, wide, and so on would nail down the time from which this wood comes with very little error. And so we have a whole new field of science. The study of time from trees, or using the Greek words for tree and time, dendrochronology. With all the subtleties involved, you can spend an entire career on the matter, and many have done so since it became a field of science in its own right towards the end of the 19th century. If we analyze every piece of wood we can lay our hands on and sequence it onto any other piece of wood equally dated, we can extend the record back and back in time if we put our mind to it. As of today, the database we have accumulated, at least for the Northern Hemisphere, goes back some 14,000 years. Now that is impressive. However, this does not mean that suffice a piece of wood from the right period, we can always tell when things have happened. You need a long sequence of growth rings, so you're probably looking at several pieces of wood from the same place and time. Also, and we'll talk a lot about that at some later date, not all trees always behave the way we expect them to. We need other ways of dating to go alongside dendrochronology, at least to put us within the right few hundred years or so. For times going back further than a few 10,000 years, we actually rely only on these. So, hey-ho, nuclear physics. To understand those modern dating methods, we need to have a brief look into what stuff is made of. Take any piece of matter at random, let's say a 20-ounce free-range Black Angus T-bone steak, and look inside closer and closer and closer, and you will eventually find that it is made up of very small things we call atoms. An atom is made up of a nucleus in the center, which essentially carries all the atom's mass, and yet is about 10,000 times smaller than the whole tiny atom itself. Around the nucleus zip a number of so-called elementary particles, electrons. The electron has a single negative electrical charge. It carries mass, albeit a very small mass, but it has no size. It is infinitely small. The nucleus of an atom is made up of particles we call nucleons, and they come in two different types, both equally large and heavy, or rather small and light, come to think of it. One is called the proton. It has a single unit of positive electrical charge. And one is the neutron, which, as the name suggests, has no electrical charge at all. For simplicity, we give both nucleons, the proton and the neutron alike, a mass of 1 atomic unit of mass. When we talk or write about elements, we use symbols. One symbol is a capital letter representing the element's name, and two numbers. One at the bottom left, which is the atomic number. That is actually the number of protons in the nucleus, which is always the same for any given element. If that number changes, we are looking at a different element. And at the top left, we write down the mass of the nucleus in atomic units of mass. Let's write down a few examples of the most common elements we find in the universe. One would be hydrogen, the simplest we can make up at all. It has just one proton in the nucleus, and so it has the atomic number of 1. And because it has nothing else in the nucleus, it has got the mass of 1 as well. Another one would be nitrogen, which has 7 protons in the nucleus, so it's got an atomic number of 7. And it's got in total a mass of 14 atomic units of mass. And another very common one is carbon, which has 6 protons in the nucleus, so it's got an atomic number of 6. And normally, it's got 12 units of atomic mass. The reason why we've chosen those particular 3 examples will become clear in a moment. The simplest atom we can construct has a nucleus made up of just 1 proton. To compensate for the positive charge, it also has only 1 electron whizzing around it. We call this atom hydrogen, and it is actually the most abundant element in the universe. It being shortly after Christmas, I managed to find a wonderful oversized proton, so I thought I might want to head out into this wonderful winter landscape and do a bit of a scale test. Let's go and place that proton where we can see it later on using the drone, and where also, hopefully, children won't go and nick it while we are walking all the way up to the Van der Waals radius. More about that later. So, where's a good place? Let's put the proton exactly here. Nice, bright and red. Should be able to find that later on the video. So, let's head out. With a bit of a walk, I want to demonstrate or illustrate a point I made earlier, and that is, in terms of spatial distribution of its mass, an atom is made up of hardly anything at all. The Christmas bauble is 100 trillion times oversized, a number that probably nobody can really imagine. I mean, I can see the zeros, lots of zeros, and I can do the maths with it, but gut feeling, No. A large number, like say 1 million, can be written as a 1, in that case with 6 zeros, or in another way as 10 times 10 times 10 times 10 times 10 times 10. So 10 times 10, 6 times over. And to abbreviate that, we use 10 with a small 6 in the upper right corner. And in words we call that 10 to the power of 6, which essentially means the 10's multiplied 6 times over. Or to abbreviate it and to speed things up, we call it 10 to the 6. There you are. That explains my number gymnastics while we were walking out to the Van der Waals radius. While we walk, let's do some quick calculations. The bauble has a diameter of 7.5 centimeters, which is 7.5 times 10 to the minus 2 meters. The proton has a diameter of 10 to the minus 15 meters, which makes it 7.5 times 10 to the 13 times smaller than that Christmas bauble. The hydrogen atom has a radius of about 10 to the minus 10 meters, and that makes it 10,000 times bigger than its nucleus, the proton. Punch all that in your calculator and you will find that with our Christmas bauble being 7.5 centimeters in diameter, we have to walk 750 meters, or just a bit less than half a mile, until we come out to the limit of our hydrogen atom, the so-called Van der Waals radius. This shed behind me, I checked on Google Maps, is exactly 750 meters away from our proton. So let's get out that drone and see if we can find it and make some sense out of the scale of all of this. What is that Van der Waals radius? Imagine a number of freely bobbing around, not chemically bound atoms of any element. They would drift around, minding their own business, but bounce off each other if they come too close. The distance from which onwards two of those need some force to bring them closer together is twice the Van der Waals radius. We could call it the mind your own business radius. I should probably be a bit vague here, but I might have been close to the legal altitude limit with that drone flight. No, but seriously, there are a lot of ambulance helicopters flying around here, and what with skiing slopes and a hospital being in close proximity, so we shouldn't go too high up. Hence the bit of backing away, turning around, closing in, which is hopefully going to give you a good authentic sense of distance between the tiny nucleus and the whole atom itself. Carbon is the fourth most abundant element in the universe, after hydrogen, helium and oxygen. Its nucleus is made up of 6 protons and, by and large, 6 neutrons, in total 12 nucleons, giving it an atomic weight of 12. To compensate for the 6 positive elemental charges of those protons, a carbon atom has 6 electrons buzzing around the nucleus at a fair distance, as we have learned. Living things contain a lot of carbon. In us humans, it provides about 1/5 of our mass. But where do we get it from? Well, we eat it. Food chains start with plants, and they get their carbon by photosynthesis. They use the sun's energy to grab carbon dioxide from the air and break it up into elementary carbon, which they tuck away in their leaves, stems, branches, what have you, and into elementary oxygen, which they release back into the air around them. Now, plants and animals and humans also release carbon while they are alive, for example by dropping leaves or by going to the toilet.
most of that stuff oxidizes and floats up in the air again as CO2, and that means that all the carbon atoms living things are made of are constantly being exchanged with the carbon in the atmosphere. All that would be only mildly interesting if it weren't for a certain twist in the makeup of elements. You see, atoms of a certain element can contain a few neutrons more or less than they really should. In case of carbon, that can be 7 or 8 instead of the nominal 6. Now, such a so-called isotope is still the same element. After all, its chemical properties, that means what other atoms it prefers to form compounds with, depend on the number of electrons, which in turn depends on the number of protons.
Around 4/5 of all atoms in our atmosphere are nitrogen, the ones with 7 protons and 7 neutrons, weighing in at a total of 14 atomic mass units. They bob about, minding their own business, until a cosmic radiation neutron comes flying in and hits one of them. When that happens, the neutron sometimes knocks out a proton and sends it flying, and the neutron gets stuck. The result is an atom which still has the same mass number, 14, because one proton has just been swapped for one equally heavy neutron. But the atomic number has decreased from 7 to 6, accounting for the now missing proton, and, remember, that changes the type of element, in this case to carbon-14. Now don't think there's a veritable firework of that stuff going on above our heads. Only about 1 in 1 trillion of all carbon atoms in the atmosphere is of the C-14 type. However few there may be, nature doesn't like that sort of thing. The carbon-14 atom has more potential energy stored in its nucleus than its more stable brother, the C-12. And so it wants to convert back into something energetically more favorable. And nature has provided a mechanism, we call it the weak interaction, to allow it to do just that. Using the weak interaction, a neutron can spontaneously turn into a proton, blasting off an electron, and another particle called a neutrino to keep lepton numbers conserved. And I'm afraid for now we need to skip what that means. Anyway, our nervous, unstable C-14 atom has thus been converted right back into a nice and stable N-14.
And so, the whole chain of chemistry involved in collecting the atmosphere's carbon dioxide into the fabric of plants, and from there on to all sorts of animals, including ourselves, and then back to the atmosphere, uses all sorts of carbon atoms until they die. From the moment a plant stops growing, stops doing photosynthesis, from the moment an animal, or your great-uncle Harry, stops breathing, they stop exchanging carbon with the atmosphere, and the fraction of C-14 within them is no longer refreshed. It then starts decaying with a half-life of 5,730 years, until such time when it is dug up and samples of that woolly mammoth, or trunk of olive tree, or thigh bone of great-uncle Harry are being put into a mass spectrometer. That is a machine which measures the atomic mass of the elements you send through it, to determine the relative quantity of C-14 compared to all the carbon we find in them. The lower that fraction is measured to be, the older the age of our sample is.
The weak interaction is called weak because it hasn't got a very high probability of actually happening. In case of our C-14 atom, it takes a very long time after it's been cosmically blasted into existence until it finally decays back into nitrogen. So long, in fact, that for any quantity of C-14 to be reduced by half, it takes about 5,730 years. We call that quantity the half-life of an isotope. Over time, the decay rate and the production rate reach to the balance I've mentioned before. About 1 in a trillion of all carbon atoms is of the C-14 type. The number of carbon-14 atoms in the atmosphere compared to the number of carbon atoms in total is already ridiculously low. Let's call that fraction N14 as we find it in the atmosphere in balance, as I said before, That is already 10 to the minus 12, 1 in a trillion. That's a ridiculously low number, but still, modern mass spectrometers will have no trouble in finding those small amounts of C-14 in any given sample. Now imagine we take a sample from something that has died a long time ago and you want to know how old it is. That would be the number of C-14 atoms, let's call it measured. That will be smaller. Let's say it's 10 to the minus 13. That means only 1 in 10 of all the originally present C-14 atoms still exists in the sample. With that, we could call the ratio x equals the number measured divided by the number originally found. In this case, x would be 1/10. And we can then calculate, knowing the half-life, how much time has passed since that sample has died and the C-14 has started to decay. In this case, T would be the half-life, 5,730 years, times the logarithm of our fraction x divided by the logarithm of 2. Punch that into your calculator and you will find with the x we've used here, we actually find that the time elapsed, in this case x equals 1/10, is something like 19,000 years. And obviously it works also for any other t up to, give or take, 50 or 60,000 years in the past. If you reach those large numbers, then the fraction of C-14 we find in our sample actually becomes so low that the error introduced to the measurement becomes ridiculously large and it all becomes a bit meaningless. Armed with that knowledge, we can now tackle lots of problems in archaeology where it is important to know exactly when something happened, or if it happened before or after something else has happened.